A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. I was looking at some old clips of GPS navigation from about 15 years ago the other day. And man, it is painful. That robotic, stilted cadence where every street name sounded like a question? Turn left on. Main Street. We've come such a long way, but it's actually made the job harder for developers because now there are too many good choices. Today's prompt from Daniel is about how to actually pick the right text-to-speech model in 2026 because the landscape has just exploded.
It really has. We've moved past the era where you just picked the one API that didn't sound like a blender. Now you're balancing model architecture, latency, VRAM requirements, and prosody. By the way, fun fact for the listeners, today's episode script was actually generated by Google Gemini 3 Flash. It's fitting considering we're talking about the models that give these AI brains a voice. I'm Herman Poppleberry, and I've been diving into the documentation for everything from the heavy hitters like 11 Labs to the ultra-efficient open source stuff like Kokoro and Piper.
Usually, when we talk about AI, people focus on the LLM, the brain. But the TTS is the face of the product. If the voice is off, the whole user experience feels cheap. Daniel's asking about the core technical parameters first. Model size, sample rate, and latency. Herman, help me out here. If I'm a developer, why do I care if a model is 100 million parameters versus a billion if they both sound fine in a demo?
Because fine in a demo doesn't scale to a production environment where you're paying for compute or fighting for milliseconds. Model size is your first big fork in the road. Larger models, like the ones powering the high-end 11 Labs tiers or the massive MARS8 family from Cambay AI, generally have a deeper understanding of context. They aren't just mapping characters to sounds, they're predicting the emotional weight of a sentence. But the trade-off is compute. If you're running a billion parameter TTS model locally, you're going to need a serious GPU, and your time to first byte is going to suffer. Think of it like a massive orchestra versus a solo violinist. The orchestra sounds richer, but it takes a lot longer to get everyone on stage and tuned up.
Right, and that leads directly into latency. If I'm building a voice assistant, I can't have a 3-second pause while the model thinks about how to say hello. That completely kills the assistant vibe. It feels like you're talking to someone on a satellite phone with a bad delay.
Well, not exactly, but you're hitting the nail on the head. For real-time applications, you're looking for models with a latency of under 200 milliseconds. This is where smaller, optimized models like Piper or Mellow TTS shine. They use architectures like VITS, variational inference, with adversarial learning for end-to-end text-to-speech. These models are designed to be fast, often running on a single CPU core. But the cost of that speed is usually richness. You lose that breathy human quality you get from the massive generative models. You get clarity, but you lose the soul.
But wait, if I'm using a cloud API, isn't the latency mostly just the network trip? Or is the model inference still the bottleneck in 2026?
It's both. Even with the fastest fiber optics, if the model takes 500 milliseconds to generate the first chunk of audio, the user is going to feel it. This is why streaming is so important. A good TTS model doesn't wait to finish the whole paragraph before it starts talking. It generates the first few words, streams them to the user, and continues generating the rest in the background. If your model architecture doesn't support efficient streaming, it doesn't matter how small it is, it's going to feel slow.
And what about sample rate? I see 22 kilohertz, 44.148. Does the average person even hear the difference over a phone speaker?
On a phone speaker, maybe not. But if your user is wearing headphones, the difference between 22 kHz and 48 kHz is the difference between a low bitrate MP3 and sitting in the room with the person. 22 kHz is the standard for most functional TTS. It's clear, it's intelligible, and it saves on bandwidth. But if you're doing high-end content creation, like a narrated book or a premium podcast, you want 44.1 or 48. Higher sample rates mean more air in the voice, more high-frequency detail that makes it feel alive rather than reconstructed.
Is there a sweet spot for developers who want quality but need to be mindful of data costs?
Usually 32 kHz is that middle ground. It's high enough to avoid that telephone compression sound, but light enough that you aren't sending massive wave files over the wire. But again, it depends on the model's native training. If a model was trained on 22 kHz data, upsampling it to 48 won't magically add detail. It just adds empty space.
It's interesting because we're seeing a split in the market. You have the cloud giants, where you just send text and get back a high-quality file, and then you have this massive surge in edge TTS.
The edge movement is fascinating right now. Look at something like Kokoro. It's a relatively small model, around 80 million parameters, but the quality to size ratio is insane. It punches way above its weight class. For a developer, the choice often comes down to, do I want to pay per character to a provider who handles the scaling, or do I want to host a model like Kokoro on a service like Modal and have total control over my costs and privacy?
Privacy is a huge one. If I'm building a medical app or a private banking assistant, I probably don't want to be sending sensitive user data to a third-party API every time the app needs to speak.
Precisely. That's where local on-device models are winning. If you can run a model like Piper directly on a user's iPhone or Android device, the data never leaves the hardware. You eliminate the API cost, you eliminate the network latency, and you gain massive trust with the user. The trade-off is that you're limited by the device's NPU or GPU. You can't run a massive 11 lab style model on a 5-year-old budget phone.
Let's talk about the non-English problem. Daniel mentioned multilingual versus language-specific models. I feel like, for a long time, English was the only language that sounded human in TTS, and everything else sounded like a bad translation of a robot.
That was the reality for a long time. But in 2026, the foundation model approach has changed that. Multilingual models are trained on dozens of languages simultaneously. The cool thing there is cross-lingual transfer. If a model learns how to express excitement in English, it can often transfer that tonal quality to its Spanish or Hebrew output, even if it has less training data in those languages.
Is there a downside to the one-size-fits-all multilingual approach?
There is. It's called language interference. Sometimes a multilingual model will have a slight, ghost-like accent from its dominant training language, usually English, even when it's speaking Japanese or French. If you need absolute native-level perfection for a specific market, a language-specific model that was tuned exclusively on high-quality data from that region will usually win. But for most global apps, a robust multilingual model like those from Cam AI is the way to go because it handles code switching. If a user drops an English technical term in the middle of a German sentence, a multilingual model handles it gracefully. A language-specific model might just choke or pronounce the English word with a thick German phonology that sounds ridiculous.
I've heard that happen. It's like the AI is trying too hard to be local. It'll say iPhone, but with such a heavy accent that you can barely recognize the brand name.
And that's a huge immersion breaker. Another thing to consider is dialect. A Spanish model might be trained on European Spanish from Madrid, which sounds very different to a user in Mexico City or Buenos Aires. Modern models are getting better at dialect conditioning, where you can pass a flag to tell the model, speak Spanish, but use a Colombian accent. It's not perfect yet, but it's miles ahead of where we were even 2 years ago.
That brings us to prosody. It's one of those words that sounds like it belongs in a poetry class, but it's actually the secret sauce for why some AI voices make you want to listen and others make you want to hit the mute button.
Prosody is effectively the rhythm, stress, and intonation of speech. It's why a question sounds like a question. It's the way your voice rises at the end of a sentence or how you pause for emphasis before a big reveal. In the old days, we tried to hard-code prosody using rules. If there is a comma, pause for 200 milliseconds. It sounded terrible because humans don't follow rigid rules.
We're messy. We speed up when we're excited and slow down when we're explaining something complex. We trail off when we're unsure.
Precisely. Modern generative TTS models learn prosody from the data. They look at the surrounding text to understand the intent. If a sentence ends in an exclamation point and starts with, "I can't believe," the model knows to shift the pitch higher and increase the energy. This is where prosody control becomes a big differentiator for developers. Some models give you style tags or emotion sliders. You can literally tell the model to be 10% more whispered or 20% more authoritative.
Wait, can you actually mix those? Like, could I have a whispered and authoritative voice at the same time? Like a spy giving orders in a library?
In theory, yes. With the latest flow matching architectures, the model treats these styles as vectors in a latent space. You can blend them. You can have a voice that is 60% joyful and 40% surprised. It allows for a level of nuance that makes the AI feel like it actually understands the subtext of what it's saying.
I've seen some models where you can provide a reference audio purely for the prosody, not the voice. Like, use this voice, but say it with the cadence of this other person.
That's the cutting edge. It's called prosody transfer. It separates the timbre, the actual sound of the vocal cords, from the performance. It's incredibly useful for things like dubbing movies. You can keep the original actor's performance, their timing, their size, their emotional beats, but swap the language and the voice to a localized version. It keeps the acting intact while changing the instrument.
One thing that drives me crazy with TTS is how it handles raw internet text. If I feed a model a tweet that has asterisks for emphasis or some weird markdown like underscores, half the models out there will literally say asterisk word asterisk. It completely ruins the immersion. Daniel asked about input text handling. Who is winning the battle against imperfect text?
This is a massive headache for developers. Most basic TTS models are dumb. They take the string you give them and convert it to phonemes. If there's an emoji or a markdown tag, they try to pronounce it. The smart way to handle this, and what we're seeing in top-tier models now, is an integrated text normalization, front end.
So like a mini LLM that cleans the text before the voice engine sees it?
Or, even better, a model that was trained on dirty text. Some of the newer end-to-end models have seen enough markdown and informal punctuation in their training sets that they've learned to interpret an asterisk as apply emphasis rather than say the word asterisk. But for developers using older or smaller models, you usually have to write a regex script or use an LLM to sanitize the input first. You have to turn 25 mph into 25 miles per hour because if the TTS says mph, it sounds like a robot.
Does that normalization handle things like dates and currency too? Because 0102C2026 could be January 2nd or February 1st depending on where you are.
That is the ultimate test of a normalization engine. A dumb model will just say 01/02. A smart model uses the locale context. If the system knows the user is in London, it says the 1st of February. If the user is in New York, it says January 2nd. This is why choosing a TTS provider isn't just about the voice, it's about the intelligence of the text processing pipeline that sits in front of it.
What about SSML? Speech synthesis, markup language. Is that still a thing in 2026, or have we moved past it?
It's still very much a thing, but its role is changing. SSML is like HTML for your voice. You use tags to say, pause here for 1 second, or change pitch to high. Traditional providers like Amazon Poly or Google Cloud TTS rely heavily on it. If you want absolute granular control over every syllable, SSML is your best friend. But let's be honest, it's a pain to write.
It's tedious. No one wants to manually tag a 1,000-word article. It feels like coding in 1995.
And that's why plain text generation with inference time conditioning is winning. Instead of using XML tags, you just give the model a natural language instruction or a style parameter. You say, read this like a news anchor, and the model handles the prosody better than you could with manual SSML tags. SSML is becoming a fallback tool for when the AI gets it wrong rather than the primary way we build voice applications. It's like manual overrides on a self-driving car.
Let's talk about the marathon runners of the TTS world long-form content. If I'm trying to turn a 30,000 word book into an audiobook, I can't just shove the whole text into a single API call. Most models have a context window for audio, right?
They do. Usually, it's limited by the attention mechanism in the transformer architecture. If you try to generate 10 minutes of audio in one go, the model starts to hallucinate or lose the voice's consistency halfway through. It might start as a deep male voice and end up sounding like a chipmunk, or it might just start repeating the same word over and over like a broken record.
So what's the strategy? Just chop it up into sentences?
If you just chop it into sentences and stitch them together, it sounds like a digital sandwich. There's no flow between the sentences. The breath. At the end of sentence 1 doesn't match the start of sentence 2. The prosody feels disjointed. The professional way to do it is overlapping chunking with context.
Break that down for me. How does that work in practice?
You send, say, 3 sentences to the model, but you also include the trailing text from the previous chunk as a reference. This tells the model, this is how the last sentence ended, so make sure this new sentence starts with the same energy and tone. Then, you use an audio crossfade to blend the chunks together seamlessly. Some modern long-form APIs, like the ones from 11 Labs or DeepGram, handle this stitching internally. But if you're building your own pipeline with open source models, you have to be very careful about your concatenation logic. If you mess up the silence between chunks, the listener's brain will immediately flag it as fake.
Is there a limit to how long that context can be? Like, can the model remember how it pronounced a character's name 3 chapters ago?
Usually, no. That's a different problem called global consistency. If you have a character named Siobhan and the model pronounces it correctly in chapter 1 but then switches to a phonetic C-Obhan in chapter 10, your audiobook is ruined. To solve that, developers use phoneme lexicons. You basically create a dictionary that tells the model, whenever you see this word, use these specific phonetic sounds. It's the only way to ensure 100% consistency over long durations.
And then there's the big one. The topic that gets all the headlines and the occasional legal lawsuit. Voice cloning. Daniel wants to know about single-shot inference versus fine-tuning. I remember when you needed hours of high-quality studio recording to clone a voice. Now it feels like I can do it with a 5-second voice memo.
The progress there is staggering. Single-shot or zero-shot cloning is what you see in most consumer apps today. You give the model a 3-second clip, and it extracts a vocal embedding, a mathematical representation of that person's unique voice characteristics. It then uses that embedding to steer the generation. The pro is that it's instant and incredibly easy. The con is that it's often a shallow clone. It gets the pitch and the general tone right, but it might miss the subtle idiosyncrasies, the specific way a person pronounces their R's or the unique rasp in their voice.
So that's where fine-tuning comes in. That's the deep dive.
With fine-tuning, you're actually updating the weights of a small part of the model using 30 minutes or an hour of that person's specific audio. This creates a much more robust clone. It captures the soul of the voice, the emotional range, the unique vocal fry, the specific regional inflections. For a brand's official voice or a digital twin of a celebrity, you always go with fine-tuning. But for a throwaway use case, like a personalized greeting in a video game, zero-shot is more than enough.
What's the compute trade-off there? I assume fine-tuning is expensive.
It's expensive up front because you have to run a training job. But once the model is fine-tuned, the inference cost, the cost to actually generate speech, is usually the same as a standard model. The real cost is the data preparation. You need clean, transcribed audio. If your training data has background noise or someone else talking, the model will actually learn to clone the noise too. I've seen clones where the AI voice consistently makes a keyboard clicking sound because the original source audio was recorded near a laptop.
That's hilarious, and also kind of terrifying. It's like the AI is a perfect mimic even of the flaws. Does it pick up things like ums and ahs too?
If they are in the training data, absolutely. Some people actually want that. If you're building a highly realistic conversational AI, you want it to say occasionally. It makes it feel more human and less like a scripted broadcast. But if you're trying to create a clean corporate narrator, you have to scrub all those verbal tics out of your training set, or the AI will replicate them faithfully.
That brings up an interesting point about style overlays. In 2026, we're seeing a move toward hybrid cloning. You take a zero-shot clone of a user's voice, but you overlay it on a professional narrator model. So you get the user's sound, but with the professional's acting ability. It solves the problem of boring clones. Most people aren't professional voice actors. If you clone their voice exactly, the output sounds as flat and boring as they do in real life. Hybrid models make us all sound like we're reading for the Oscars. I could use that. My morning voice is not something anyone wants to hear for an entire audiobook.
You and me both, Corn. But look, if you're a developer listening to this, the golden rule for 2026 is don't over-engineer for quality you don't need. If you're building a notification system for a factory floor, you don't need a 48 kilohertz, fine-tuned generative model with emotional prosody. You need a small, robust, low-latency model like Piper that can run on a Raspberry Pi and survive a lost internet connection.
But if you're building a companion, AI, or a high-end storytelling app, cutting corners on the TTS is the fastest way to lose your audience. People have a very low tolerance for uncanny valley voices. As soon as the voice feels wrong, the suspension of disbelief is gone, and they stop engaging with the content.
That's the Turing trap of voice. The closer you get to perfection, the more jarring the remaining flaws become. If a voice is obviously a robot, we forgive it. If it sounds 99% human but mispronounces one word with a weird metallic glitch, it's creepy.
One area we haven't touched on much is the input processing for non-textual cues, like how do models handle laughter or sighing in 2026. I've seen some demos where the AI actually chuckles mid-sentence.
That's the non-verbal communication frontier. This is largely handled through tokenization. Just like LLMs have tokens for words, advanced TTS models now have vocal tokens for things like breaths, laughs, clears throat, or even hesitation sounds like and If you're using a model like Chatterbox, you can actually insert a tag for a short laugh, and the model will synthesize it naturally into the vocal stream. It's not just playing a sound effect, it's generating the laugh using the same vocal cords as the speech.
That's a huge deal for naturalness, because a real human doesn't just stop talking, play a laugh.wav file, and then start talking again. The laugh bleeds into the words. Your voice is shaky for a second after you laugh.
That co-articulation between speech and non-speech sounds is what makes the top-tier models like 11 Labs feel so alive. They understand that a sigh isn't just a sound, it changes the airiness of the next three words. For developers, the takeaway is to look for models that support phonetic and non-verbal tokens if you're doing anything conversational.
So, looking at the practical side for a second, if someone is starting a project today, what's the stack you recommend? Because you've mentioned a lot of names.
It depends on your budget to quality ratio. If you have infinite budget and want the best quality, you go with 11 Labs. Their API is the industry standard for a reason. The prosody is unmatched, and the voice library is massive. If you're privacy conscious or cost sensitive, you look at the open source world. Kokoro is the darling of the community right now because it's so lightweight and sounds great. If you need massive scale with low latency, something like DeepGram's Aura is built specifically for that. It's sacrifice some warmth for extreme speed.
And don't forget the middleware. There are services now that act as an aggregator for TTS. You write your code once, and you can swap between 20 different providers with a single config change.
That's a smart move for future-proofing. The king of the hill today might be obsolete in 6 months. We saw it with the jump from the old concatenated models to neural models, and now we're seeing it with the jump from autoregressive to flow-matching architectures. Being able to swap your voice engine without rewriting your entire application is a massive competitive advantage. It also lets you AAB test different voices with real users to see which one converts better.
We've covered a lot of ground, from the physics of the audio like sample rates and latency to the psychology of it like prosody and emotional weight. It feels like the voice AI world is finally catching up to the text AI world. We're moving from making it work to making it beautiful.
It's an exciting time to be an ear, Corn. We're finally reaching the point where the digital assistant doesn't sound like a piece of software. It sounds like a person, and that changes everything about how we interact with technology. It becomes less of a tool and more of a presence. Think about how much more likely you are to follow advice from a voice that sounds empathetic versus one that sounds like a calculator.
Hopefully, a presence that knows how to handle a me-age abbreviation without sounding like it's having a stroke.
One can only hope, but with the right model selection, that's a problem we can finally leave in the past. We're getting to the point where the AI can infer the meaning of ambiguous abbreviations just by looking at the context of the sentence, which is a huge relief for developers everywhere.
Well, I think that's a pretty solid roadmap for anyone trying to navigate the voice jungle. Huge thanks to Daniel for the prompt. This is one of those topics that changes so fast that you really have to check the state of the art every few weeks.
It's a full-time job just keeping up with the GitHub repos. But that's what makes it fun. Every Tuesday there's a new paper that claims to have solved some impossible latency problem or added a new layer of vocal realism.
If you're out there building something with these tools, we'd love to hear about it. What are you using? What's the edge case that's driving you crazy? Are you struggling with technical pronunciations or trying to get the perfect emotional sigh? Drop us a line.
Thanks as always to our producer, Hilbert Flumingtop, for keeping the gears turning behind the scenes. And a big thanks to Modal for providing the GPU credits that power the generation of this show. Without that serverless compute, we'd just be two animals talking to ourselves in the dark.
Which, to be fair, we basically are anyway. This has been My Weird Prompts. If you're enjoying the deep dives, a quick review on your podcast app really does help us reach more people who care about this weird intersection of tech and humanity. It helps the algorithm realize we aren't just robots ourselves.
Find us at myweirdprompts.com for the full archive and all the ways to subscribe. We've got links to all the models we mentioned today in the show notes.
See ya?
Goodbye.
This episode was produced using Google Gemini 3 Flash, text-to-speech by Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My Weird Prompts, that's the flows from slow